in the series of practical workshops on mineral identification in hand specimen. And tonight we're going to look at some light coloured minerals. We'll do a little recap from last time first. Remember that if you want to look at hand specimens, it's a good idea to have a reasonable sized piece of stuff to look at, because then you can get a good representative idea of what's in there. We'll do a recap. We'll do something on mineral crystallization, and that was quite a lot of what I was writing on that post on the Facebook page, group page for John, but we'll go over that since not everybody has seen that. And then we'll go into the light coloured minerals. Right, last time, well, we learnt to identify quartz, olivine and plagioclase. Quartz and olivine, they should be relatively easy to identify because they have this granular habit, what we call anhedral. They are glassy. They've got a glossy sheen to them. They are either transparent and colourless, or they are green and transparent. Green is the olivine generally. Remember, that's not always the case. And quartz, again, quartz is not always colourless. It can be pale grey at times. We learned to identify plagioclase. That was sometimes colourless, or it could be a variety of colours, transparent to translucent, a sort of white, generally speaking. It's got a satin luster to it. Now that's sort of not exactly a shiny glossy, but sort of sub-shiny, sub-glossy. And satin is the term that we tend to use. If you satin finished steel is exactly what it is. And the plagioclases generally have got good crystal shape. We call that euhedral, good shape. And the lath-shaped crystals, remember, those are definitive. So all these plagioclases have got those lath-shaped crystals. And when we're looking at the qualities that we can use to identify minerals in hand specimen, we've got things like the crystalline nature, the colour. You've got to be careful with that. The crystal habit, or the shape of the crystals, the luster. We've said that the plagioclases have a satin luster. And we've got the transparent, translucent and opaque qualities, something that we call diaphaneity. And we have something, we didn't talk much about cleavage last time, so we'll say a little bit more about cleavage when I'm talking about crystallization. And again, we just touched on this idea about association last time. What that means is if you've identified a particular mineral in your rock and you've got something else that you think you've identified in that rock which doesn't fit with the mineral, the other mineral that you've identified, i.e. the association isn't right, so that is one part of the problem solved, because if you look at the association of these minerals, then that's a way to get through this problem. Is this that mineral, or is it something else? Right, and we'll have a little bit more of an example with these associations in a moment. Right, let's first of all look at mineral crystallization and crystal shape. We've got an ideal situation and what we actually get in reality, and the two sometimes are quite different. And these can end up giving us things that we call subhedral crystals, and these are crystals that don't have an ideal shape. So they're not what you'd expect from looking at the various symmetry axes and so forth in the crystals. Right, this is those of you on the Facebook page will have seen this. These are the series of crystal systems. These are the ideal crystal systems. And what these are all to do with is the arrangement of the atoms within the crystal lattices. And it's governed in a way by by ionic size. And if you substitute different sized ions into a crystal, you can actually push it from one system into another system. For example, in the plagioclases, a lot of them are monoclinic, a lot of them are triclinic. And depending on what you've got, whether it's triclinic or monoclinic, depends on the size of the other ions that you are substituting in your solid solution series. We'll talk a little bit more about that in a moment. So these are the ideal crystal shapes, but you're not going to see things like this in reality too often. And the reason is because what we have are modifications. Here's an orthorhombic crystal that's got a modification up that corner there and along that corner there. A triclinic system here, that can have a modification there, can have a modification here. As an orthorhombic system that's got something that we call a pinacoid modification here, and on the reverse face behind, that's got another truncation, which is a pinacoid face. We have, there's a hexagonal system, but you can have these faces planed off with modifications. So ultimately, the thing doesn't necessarily really look like a hexagon. And we have this, another orthorhombic crystal that's got domes. These are domes on the terminations, one set there and one set down there. And really what governs what developments you get, it can in part be due to some impurities within the crystals, but generally it's just nature. Nature does one thing, then it'll do another thing. So the amount of variation can be quite significant. And what this means is that when you look at minerals, one thing will have one shape, and the same mineral can then have another shape as well. So you need to be aware of that. Right, let's look at crystal orientation, because when we look at hand specimens, we're really looking at how the crystals are orientated. And this is an ideal view where we've got all the mineral axes are all aligned with each other. You can get this situation under particular conditions, but it is very rare. And what happens most of the time is that you're going to get this sort of arrangement. The technical term for this is higgledy-piggledy. And what it means is that when you're looking at the surface, the mineral surface will be around here. What it means is that you're going to be looking at sections through bits like that. You're going to be looking at more longitudinal sections. There's another longitudinal section. So you're going to have all sorts of orientations of your crystals. Even if they are ideal crystals, you are still going to have a range of different orientations, so they are going to look different. And I think John Burns put that picture up from Cornwall, where you had hexagonal feldspars when you're looking end on into bits like that. So you're looking into there. And there were also the lath-shaped crystals along there. So those are things you really need to be aware of. Right, if we move on to how do we make crystals? Crystal growth and this thing called twinning. Well, we start off, we have to have some point where the crystal can grow. It's called a nucleation point. And this nucleation point can be, it can be a foreign particle within the fluid that is beginning to crystallize, or it can be some cluster of ions that are beginning to associate together under chemical bonding or electronic bonding. Well, once you've got a nucleation site, then that nucleation site attracts the various ions towards it to grow the particular crystal. Now, the not ideal situations are when you've got other ions getting in the way. And as you are crystallizing from your fluid, your magma, which is where these are coming from, the ions are collecting. They're not all the same ions. They're not all the ones that are going to form the particular mineral that you are growing. There will be all sorts of other ions. And sometimes they can really get in the way of the ions you are trying to use to build your crystal. And you know what, they actually push out the ideal ions that you're trying to accrete to make your crystal. And this will result in things that we call crystal dislocations. So the bonds between the ions are not in a regular fashion. They suddenly dislocate. And that is caused by these other ions that are getting into the way. Now, allied to this ions getting in the way, we have another stage which are called intergrowths. And this is where we have two very similar minerals that are crystallizing at the same time. So these are co-crystallizing, and they will give you a series of two different minerals alongside each other, what we call lamellae of alternating minerals. And the best example of this co-crystallization is where we have sodium plagioclase and alkali feldspar. Now, the chemical compositions of these two, of alkali feldspar and sodium plagioclase, are quite similar, and their melting temperature is quite similar too. And they got similar ionic sizes. And so it's quite plausible that these two minerals, as they are growing, will take up similar amount of space. And what happens is that we get layers of the sodium plagioclase and layers of the alkali feldspar, one on top of another. And this is called a perthitic texture. Now, it's not easy to identify perthitic texture within hand specimens. You can do it sometimes, but not always. It has to be very well defined to be able to see it. But it does come to light when you're looking at thin sections under the microscope. But I mention that there because it is one of these issues where we are looking at intergrowths of various minerals. Now, allied to that is this concept of twinning. And what twinning is when a crystal is growing and accreting ions, there will suddenly be, it's either triggered by a dislocation or some inhomogeneity in the process of crystallization, that same mineral will start to grow on the accreting mineral with a slightly different orientation of its atomic arrangement. It's the same mineral and it's growing in this, well, alongside the first mineral, the same chemistry, but they have different orientations of their crystal lattices. The lattices are the same, so the lattices are the same, but the orientation of one compared with the other is slightly different. And we'll see the manifestation of that when we start looking at twinning shortly. Now, there's one characteristic type of twinning that's very common in plagioclase. And if it's visible, it's a very, very fine grooving, parallel lines, straight parallel lines. It's what we call record groove twinning. But thinking about that title, record grooves are circular. And plagioclase twinning is not circular, there's straight lines. And I guess in the future, it's going to be a case of saying to people, well, you see this twinning, that's how we used to have audio media way back in the 20th century. So a name that's going to go out. But it manifests itself in a number of very, very tiny grooves. Now, there is a particular manifestation of this in some of the plagioclase feldspars, because the spacing between the individual grooves acts like a diffraction grating. And in things like labradorite, for example, you might not be able to identify in hand specimen, even with a hand lens, you might not be able to identify this record groove twinning, but because the twinning is there and it is acting like a diffraction grating, you will see a play of colors on your specimen. So the labradorites will have this play of colors, bluish, greenish colors. And the term is actually called labradorescence. So that's something to remember if you're looking at particular plagioclases. Now, when we look at the alkali feldspars, which we will be doing very shortly now, that has what we call simple twinning. And as the name implies, it's not as complex as the record groove twinning. And we'll see examples of simple twinning shortly. Now, if we can pick up the simple twinning, it does help in our identification of alkali feldspars. Right, and remember now, we're going to talk about the alkali feldspars, but this is the classic shape of feldspars, that lath-shaped crystalline shape. There's almost a hexagonal bit there, some semi-hexagonal things there, just to point these out, since John identified them in the Cornish granite. So these are hexagons in there, as well as the elongate long axis orientations. Now, when we looked last time at the plagioclases, we had, you remember, a variety of colors, and these were often either transparent or translucent. With alkali feldspars, we've got a greater range of colors, and there's only one color rule with feldspars, and that is plagioclase is never pink. You will never ever get pink plagioclase, just doesn't happen. So if you've got something pink, you know it's got to be an alkali feldspar. Well, something, at least something different. It's not a plagioclase. Right, let's look at this mineral. There we go. There is a pink, look at the scale bar. So that's quite a large crystal. That's a 1 centimeter scale. So these are a couple of centimeters in size, this crystal here, but it's browny pink. So that, and again, look at the lath-shaped crystal shape. That's lath-shaped there. That is an alkali feldspar crystal. And there's another one there. Look at the lath shape of that crystal there. And there's some there. There's a different orientation in there. There's a more elongate bit there. That's an oblique section there. There's an elongate one there. And we've got smaller pink examples within this ground mass. Now, I think we momentarily talked about these large crystals, what we call phenocrysts. We mentioned that word briefly last time, but we'll go over it again now. And phenocrysts are, well, large crystals. And they are large because they have grown somewhere else. They have had plenty more time to grow than the ground mass alkali feldspar crystals, like these little bits here and all this stuff, all this pink stuff here. And so there's been a 2-stage cooling process of this magma deep within the Earth's crust, so it's a slow cooling, but this will have begun to cool possibly within its magma reservoir, have begun to precipitate out some of these phenocrysts, these larger crystals of the alkali feldspar. And the overall texture of this rock, we call it porphyritic. Now, this is a porphyritic texture. So lots of pink alkali feldspar. Now in this rock, we've also this white stuff that, because it is, let me find a lath. There's a lath there. There we go. It's not translucent, it's not transparent, it's white. There's another one there. Possibly a bit there. Possibly there. Oh, look, there. There. Now, I've just seen this. This is a brilliant example of simple twinning. This is the whole mineral crystal. And this dividing line between the darker and the lighter is the twin plane. So this piece, it's all alkali feldspar. It's got this satin luster. It's opaque and it's white colored. But that, because it's got a different set of optical properties in terms of reflecting the light, it's got a slightly different color to it. And the demarcation between the two different colors is the twin plane on that crystal. So there's the twin plane down there. And that's how you can identify these simple twins. One side will reflect the light in a slightly different way to the other side. So that is a simple twin in a white alkali feldspar. Now, I can't find any other ones, but that was fortuitous. I've not noticed that one before. So there we've got phenocrysts of alkali feldspar, and we've also got these white alkali feldspars as well. Let's move on to the characteristics. So from what we've just seen in that rock, euhedral to subhedral, yeah, that's what we're looking at. The lath-shaped crystals, as we've seen, opaque and white, yeah, we've seen the white ones. Pink brown, it can be pale red, they can be pale red. They can also be grey, and we've got examples of the grey ones in a moment. And they've got this satin luster, so that's another one of the characteristics. And as we've just seen, fortuitously, we've got simple twinning. Not all crystals are going to be simply twinned. If it is developed, or if you can see it, then it's a good identifier. So that's a rundown of the characteristics of the alkali feldspars. Let's look at some more. There's another porphyritic rock. Here's a nice pinkish brown alkali feldspar phenocryst. There's some more here. There's some nice ones there and there, nice ones there, nice ones there, nice ones there. And this material, this white stuff, because it's opaque, it's got that satin luster to it. This is a white variety of alkali feldspar. Look, there's some nice lath-shaped crystals there, lath-shaped crystals there, lath-shaped crystals there. So this rock has got these pink alkali feldspars and white alkali feldspars as well. I'm not sure, I can't see too much small pink in the ground mass. Maybe there's some possibly down there. I'm not certain about that. But certainly we've got nice pink phenocrysts of alkali feldspar, and the smaller ground mass white opaque satin luster alkali feldspars. There's your scale bar just for guidance. Right, let's move on. These are white. These are bleak sections of the laths. Look at this is what I mean by the satin luster. These are quite big. There's your scale bar, 1 centimeter there. That's the satin luster for alkali feldspars. And again, these are white, opaque, and that satin luster. Can I see any twinning? Not instantly.
I lost connection.
Can't see any instant twinning. Another section of some alkali feldspars there. And here we've got some, there's the scale bar, that's a 2 centimeter scale bar here. And see here's some quite big grey alkali feldspars. And I think we've got some almost hexagonal ones in there. There's some almost hexagonal sections or crudely hexagonal crystals in there. That's some, might be a bit of a lath. But this is the grey alkali feldspar in that rock there. So these are quite large crystals. And then we've got the terminations. See the terminations on that top face as well. Right, we talked about twinning, and as I say, fortuitously, we managed to find some twinned alkali feldspar in that first rock we were looking at. But we've got another one which is possibly a little bit more obvious, and that's this one here. Look at the scale bar for a moment. That's your 1 centimeter scale. So these are a couple of centimeters in size, so quite big beasts, these. And what I've done, I've moved the sample so that the sunlight is reflecting on one face, so it's reflecting off this face as opposed to this face. But this is all the same mineral. It's the same piece of alkali feldspar. But as I say, the crystal, the lattice orientation is different from this piece to this piece. And that's what we mean by twins. It's the same chemistry, it's the same crystal, or it's a crystal growing along the twin plane of this alkali feldspar. Now what I'm going to do, I'm going to change the light a little bit. There we are, it's come back here again. So you see, I've arranged so that we're not reflecting too much on this face now. But when you get particularly these large phenocrysts of alkali feldspar, if you think you've got alkali feldspars and you're trying to identify them, take the rock and just move it around in light, sunlight preferably. And if you start to see the variations in reflecting surfaces like this and that there's a line between them, the division between one type of reflection and the other type of reflection, then that is simple twinning. And you've got simple twins. And if you've got simple twins, then it's an alkali feldspar. Now I'm just looking at this one. There might be a possible twin plane there, but it's not as obvious. I can't see any more. So that's the twin plane of an alkali feldspar, and that is simple twinning. And that, if it's there, if it's developed, and if you can see it, that is characteristic of the alkali feldspars. Right, we've got an issue here with the identification of quartz, plagioclase, and alkali feldspars. And it's a conundrum. And here we need to look at associations. Last time we were able to identify the difference between quartz and plagioclase. So if we had plagioclase that was poorly crystalline, it was a bit, well, either anhedral or slightly anhedral, because it had that slightly more satin luster as opposed to the much more glassy quartz, then then we could identify the glossy, glassy quartz and the slightly more satin, translucent plagioclase. But we're now going to throw a sort of spanner into the works and bring in alkali feldspars. And we're also going to look at this thing about associations. The rocks containing quartz and plagioclase are not common. So if you think you've got plagioclase and quartz in a rock, maybe you need to, have a good look at your sample, because it is a fairly uncommon situation. And rocks that do contain quartz and plagioclase are things called plagiogranites. So that's the blanket term for these things. Now, the research I'm doing in Cyprus, well, when I was doing research in Cyprus, that's all I was looking at, plagiogranites. So all my samples got quartz and plagioclase in them. But you're not likely to come across any good rocks that have got just quartz and plagioclase in them. But you can have, and these are much more common, you can have quartz, plagioclase, and alkali feldspar in the same rock. So if you think you've identified quartz and plagioclase, you can look around for alkali feldspars as well. And that will allow you to develop your skills at being able to identify minerals in hand specimens. Right, let's look at an example. Here we've got, it's that same one that we looked at earlier on. We've got some quartz arrowed, I can find my pointer, which has just disappeared. Well, the top arrow is identifying a bit of quartz up there. There's another bit of quartz. Now, thing to notice here, and this is quite common when you've got quartz within rocks that are quite light colored, the quartz can become slightly more gray when you're looking at it. But this is much more glassy. These bits here are much more glassy. Where have I got more? That's possibly a bit there. That's glassy and grayish. So anyway, so those are quartzes. Now, if you look here, you've got some more translucent, slightly more elongated, non-granular material, and that is a plagioclase. But here you've got some elongate satin luster crystals, and it is this one here, that and this one, these are alkali feldspars. It's also slightly pinkish. In fact, maybe this bit is a separate piece to this piece. But, oh, and there's a bit of quartz in there as well. See that bit of quartz there. So in this rock, you've got your granular glassy quartz, which is slightly grayish here, but it's very glassy and glossy. You've got your elongated, slightly less glossy, slightly more satin luster plagioclase, and you've got your opaque satin luster alkali feldspar. So you can have all those three together, and this is an example of that sort of rock. And I think this is quite good to be able to determine the difference between these three minerals in this rock specimen. Right, let's move on to this one. Slightly more difficult. we've got, again, yes, here's the quartz. This bit here, that's quartz. It is granular. It is slightly more grey, and it is glossy, glassy even. And remember, that glassy term is a good term to use when you are talking about quartz. We've also got the glassy. I'm just trying to look for some more quartz. There's some more quartz in here. I can't pick it out instantly. Can't see it. This big piece in the middle, this big piece here, that is opaque. It's white, so that's an alkali feldspar. This is nicely translucent satin, slightly less glossy than the quartz, so that is plagioclase. That one there is less glossy and translucent than this plagioclase, so that is alkali feldspar. That's alkali feldspar there because it's not translucent, it's more opaque. It's got that satin luster to it, and it's got that elongate shape. There's another elongated, non-translucent or opaque one there. This material here is alkali feldspar because it's opaque. And find some more, there's some translucent down there. So that's plagioclase. So that's giving you a bit of practice at looking at the difference between alkali feldspar, plagioclase, and quartz in the same rock. So quite a lot of potentially useful stuff there. Right, recap on all this this stuff here. Plagioclase is transparent to translucent. It's less glassy than alkali feldspar. The alkali feldspar is opaque, but they both got the satin luster. But when you've got the translucency of the plagioclase, you can't always see that. But as we've identified just now, the plagioclase won't be pink. No way will it be pink. And the alkali feldspars we can recognize because they've got, well, if it's developed, they will have simple twinning, whereas the plagioclase will have this record groove twinning on it. Now, as I said, the rocks containing quartz plus only plagioclase, those are uncommon, so you're very unlikely to come across those. However, the quartz, plagioclase, and alkali feldspar is much more common, and you'll find this in some things that are actually called granites, but they're not granites. There's something called monzonites, but they are sort of granites. That's why it's in inverted commas. So those are your alkali feldspars, and like I say, if you're looking at anything granitic, you will have quite a lot of all these three minerals in them in your hand specimen. Right, let's move on to the other light colored mineral that I want to look at now, and that is white mica. There's some white mica in this sample. Look at your scale bar. That's your 1 centimeter scale bar there. The first thing that is possibly noticeable is that, well, it's the light color. White mica is silvery. It is very silvery. And all these bits in here have this silver color. The habit, it's in the hexagonal system, but you'll never, well, very, very rarely will you see hexagons. Possibly there, that might be a hex, well, sort of, but it's very generally poorly developed. But you will find lots and lots of flakes which have a very glossy luster to them. It's what we call a metallic luster, or even a plastic luster. If you can remember Back in the day, Formica worktops had that sort of shine to the surface. Well, that's what micas, these white micas, it's that sort of glossy, we call a sort of a plastic luster to them. But they occur as flakes, little flakes and flecks, and this silvery color. Let's look at another one. Again, there's the scale bar down there. Yeah, all this flaky, these little flecks. There, 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 there. There are lots of little flecks of white mica. Now, you will come across the term muscovite given to white mica. Muscovite, and it's really following on from Eileen's question, what's a mineral? Muscovite, you can write its chemical formula, well, I can't, but you can write its chemical formula out. Now, if you know definitely through various spectrographic techniques that this has got the chemical formula of muscovite, you can call it muscovite. But if you don't know what its exact chemical composition is, and you won't know its exact you won't know its chemical composition by looking at it in a hand specimen, you will call it white mica. Muscovite has its own specific chemical formula, and you can only call it muscovite if you know that it has got that chemical formula. So don't fall into that trap. Here's another so there's little flecks, look, silvery flecks. There's your scale bar down there, and these little silvery flecks, flecks and flakes is how white mica occurs. And these little bits here dotted about in there and around there. So those are white micas. On a large scale, there's your 2 centimeter scale bar. Quite large developments here. This is a rock type called a pegmatite, which just has large crystals, and the silvery sheen, very noticeable on all these pieces here. Very reflects light very well. And flaky, like sheets even, some sheets there. And when you get lots of sheets together, it looks like this. And these are actually things that we call books of mica, because they look like looking end on at books. And these are the leaves of paper in a book, or they're actually leaves of mica, of this white mica. And so that's the typical color of these white micas. Some more here, there's the silvery color of this piece. Again, these are very large crystals. We've also got little flecks of mica here, white mica dotted around there. Now, in terms of associations, you're likely to find white micas in the same situations that you find things like quartz alkali feldspar, i.e. granitic or felsic rocks. That's the common place where you find them. But you can also find white micas in metamorphic rocks. We haven't talked about metamorphic rocks yet, which we will do in a subsequent workshop. But you'll find that white mica is a dominant mineral in mica schist, where again you can develop very large crystals dependent on the conditions of formation of the metamorphic rock. So that's large white micas. So what about white mica? Well, light colored, very silvery, as we've seen. It's transparent. When you get thin flakes, it's actually transparent. You can see through it. But when you've got three or four flakes or layers building up, then it becomes a bit more translucent. Very shiny. It's got this metallic or plastic glossy luster to it, and generally it'll be as thin flecks and flakes, but you will find these books of mica if it's plentiful. Like I say, you should have a hexagonal shape, but you'll not see that, generally speaking, in rocks. It's also quite soft. So if you've got a penknife and you've got some large stuff, it'll scratch very easily, and you can bend it. You can bend it as well, so it's flexible. So those are the white micas. There we go. There's a final look at some of the white mica again. Lots and lots of sheets full of this silvery, very noticeable rock. Right. Okay. So what have we learned? Well, we've found a bit out about mineral crystallization, how it happens that we get nucleation. It doesn't always go according to plan. We get all these dislocations in crystals sometimes. It's got the possibility for crystallizing within the same mineral but at a different crystal orientation, same mineral but different orientation, which will generate twins. We can have non-ideal crystals if other ions get in the way, so they can modify the shape away from the ideal. We can have modifications to the ideal crystal shape by nature. And the property of cleavage, which is about the mineral planes and where we can get fractures within the rock. I didn't mention the cleavage of the feldspars, but there's normally a longitudinal fracture pattern and one at what appears to be 90 degrees. It isn't 90 degrees, and it can't be 90 degrees because all the feldspars are either triclinic or monoclinic crystal system, and the axes are not at 90 degrees. In fact, the plagioclase is, I think, the deviation from 90 degrees, something like 2 degrees. And of course, with the naked eye, you can't detect that difference. So they would appear to be two cleavages at 90 degrees, and the mineral will fracture along those planes within the crystal. The only way you can identify completely is under the petrological microscope, where you can actually measure the angles. Right, we've also learned to identify the alkali feldspars, that lovely satin luster. They're opaque. They've got that elongated shape, generally speaking, and we can have simple twinning. And distinguishing it from plagioclase feldspar, you've got the plagioclases being more translucent, still with that satin luster though. And if you've got the twinning developed, it will be the record groove type of twinning. And finally, we've learned to be able to pick out what white mica looks like and build up our inventory of igneous rock minerals. So next time we're going to look at some dark minerals. So I'll now open up this session and let's go over to some questions.